Okay, in this video, I'm going to do a little bit of review of electrons, electron configuration, and I'm going to do it by just taking a look at iron. And if I took a look at iron, iron has 26 electrons. And this means that in a neutral iron atom, I have 26 protons, 26 electrons. But how are the electrons arranged? Well, I'm going to go through, first of all, the orbital diagram for it, because out of the 26 electrons, 2 of them are going to be in the 1s. And remember, we can represent those with the half arrows. So that's 1s. And then we have the 2s. Again, a up and a down half arrow. The 2p is higher in energy than that. Now, there's not a huge difference between those, but the 2p is actually higher than the 2s. And I've got my 3 electrons there, 3 electrons there. And when I fill, I put 1 in each because then I have less electron repulsion before I pair up. That's called Hund's rule. Then we're going to have 3s and then 3p. Again, 3p is higher than 3s. Not a huge amount. I'll make that a little bit more exaggerated on the difference just so that we can see it. And that's full. So if I notice, I have now 8 electrons in the 3p. Now, I can hold more than 8 electrons in the third energy level, but not if it's in the valence shell. So when I start adding more electrons to it, we're going to add electrons to the 4s first, and then we're going to add them to the 3d because the 3d is higher in energy than the 4s. In the 3d, I have 5. I didn't leave myself very good space here, but you can still see it. And I now have 2, 4, and 6 are 10, 12, 18, 19, 20. I have 6 more to place. 1, 2, 3, 4, 5, 6. Now, for these electrons, I could go through and I can do a number of things. One of the things that I can do is take a look at the differences in energies, look at transitions between things. And this is how, if I have something going from a higher energy level to an lower energy level, it's going to emit radiation. But we're not going to look at that right now. We're going to look at something called quantum numbers. Now, the quantum numbers are really simple. They are useful for some very complex calculations, but there's some really simple things. First of all is the energy level, what we call N. N is the energy level. And this tells us which energy level an electron is. So I am going to take a look at one particular electron, and I'm just going to look at this last one that we drew here. And for this one, the energy level is 3 because it's in the 3D. That 3, that's our energy level. Now, I also have different types of orbitals, and the orbitals have to do with the shapes of the probability regions for the electrons. An s orbital is spherical. No, s does not stand for spherical. P is going to be more of an hourglass shape. D, we're going to have kind of 4 lobes with that, except for the dz squared. And then we have f orbitals. So we'll have 1s, 3p, 5d, we would have 7f. But for the second quantum number, L, is basically going to be based on S, P, D, or F. S equals 0, P is 1, D is 2, F is 3. This particular electron is in a D equals 2. And then I have ML, which is the magnetic quantum number. It tells me which of these orbitals it's in. And one rule, N always has to be greater than L. The second set we have is ML can be anything from negative L to L. So if L is 0, I can go from negative 0 to 0. Well, that makes sense because the S only has one orbital. There's only one possible number for ML. For P, where L equals 1, it's negative 1, 0, and 1. 3 numbers, 3 orbitals. For D, I have negative 2, negative 1, 0, 1, and 2. Now, these are arbitrary. You know, if I hold this way up, I could hold it this way up. This doesn't change, but the way that I look at it does. So these are arbitrary, but they're still important for us to establish something. We'll know very specifically they're different. So this particular one is in the blank that we call a negative 2. And then finally, the fourth quantum number is the spin. Now, think of something spinning like a top spinning and it's processing one way or spinning the other way. I look at it, you have an electron here and another electron here, and if they're in the same orbital spinning in opposite directions, there's less repulsion and they can actually be in the same orbital. Again, that's just a simple visual for us to be able to understand something that we really don't understand. So it's just a very simple model. We're going to represent up arrows with a positive 1/2, down arrows with a negative 1/2. This particular one is a down arrow. So I'm able to set a set of 4 quantum numbers for this electron right here. Now, for the entire atom of iron, I would have to have one set of quantum numbers for this one set of quantum numbers for this one here, one for each of those. I would have 26 different sets of quantum numbers, none of which would have an identical set of 4. That is the Pauli exclusion principle. And that is how we can remember our electrons. There is a simplified way that we can do this called the electron configuration. And for this, we're going to call it 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. And that is the electron configuration for iron. Now, if I look here, that is the electron configuration for one of our elements that is a noble gas, and that is argon. So I could do this and write my electron configuration. Whoops, that's just supposed to be a bracket. And I know you're thinking, argon, all those are argon. No, they're still there. We're just representing it with a noble gas. So this is our electron configuration, orbital diagrams, and a brief review of quantum numbers. Now, we'll also take a look in this same video a little bit at some periodic properties, because as you go to the right in the periodic table, the atoms don't get bigger, they get smaller. So why is that? Well, it has to do with the nucleus. And if I take a look at the nucleus, if I take a look at, say, let's look at nitrogen and oxygen. Nitrogen has 7 protons in the nucleus. Oxygen has 8 protons in the nucleus. But yet they both have, and I'm going to draw the very bad model, where I have 2 layers of electrons, okay? First energy level contains 2 electrons. Second energy level will contain 5 here. In this one, the first energy level contains 2. The second one contains 6. And I'm just going to draw some E's here just so we know. Just so we have a reference there. Now again, this is a very bad model of the atom, but it's going to help make our point. Now if I look here, this electron in the outer shell is only affected by this inner shell. We call those shielding electrons. Okay, so this electron is shielded from the nucleus, which has 8 protons. This one is shielded from the nucleus, which has 7 protons. But the shielding is only a layer of 2 electrons in both cases. We say that the difference between that, the number of electrons in the shielding electron will cause a lower nuclear charge to be felt by these electrons. We call that effective nuclear charge. Protons minus shielding electrons. This has an effective nuclear charge of a +5. This one would have an effective nuclear charge of a +6. This electron feels the pull of 6 protons. This one feels a pull of 5 protons. So this is going to be smaller. This is why atoms get smaller as you go to the right in the periodic table. As you go down, we start adding more and more layers, and that's why they get bigger. Okay, so that is a simple review of the size. There are some other periodic properties that depend on it. Among those are ionization energy, that is the energy to remove an electron. I'm not going to have time to go through that here right now. I do recommend that you go through that. And you can also look at the size. If I lose an electron, I now have more protons than electrons. That's going to make it smaller. If I add an electron, if I make it an anion, I've added electron repulsion without adding any more attraction in the nucleus. So anions are larger. All right, so that should be a good review. You will know by this point whether you need to go back and review things like ionization energy, etc. I recommend that you do, but I'm not going to do that in that video now.